began to see in our previous sections how you can have a reversible step. You might have seen reversible next to slow or fast before in a mechanism. So a common type of reaction mechanism is one involving a first step in which both the forward and reverse reactions are very fast compared to the second reactions in the second step. So let's look at, for example, the decomposition of ozone to oxygen. A proposed mechanism is shown below, and then the observed rate law is also given. Now note here, do you see how in the rate law the product is involved? That hasn't been a part of what we've seen so far. And this is very unusual, but that is what has been observed. That's what they saw by experiment. So we have these two steps for the mechanism to decompose the ozone into oxygen. So for this mechanism, we assume that both the forward and reverse reactions of the first step are very fast compared to the second step. So if you look at the forward and backward arrow, the K1 and the K negative 1, the K1 would be the rate constant for the forward reaction, and K negative 1 would be the rate constant for the backwards reaction. So just so that you see how that works, we could have, this is for the forward, we would have the rate law be rate is equal to K1 times the concentration of the ozone. And for the reverse reaction, the rate would be equal to K negative 1 times the concentration of O2 times oxygen. Okay? Now, we don't like to include intermediates usually in our rate laws, so that pulls up a red flag. Okay? So, when we know that we're assuming that the first step is very fast with the forward and reverse reactions, then that means that the second step is the rate determining step. So the second step, which I hadn't written, but for this one right here, the bottom, that rate law is what the overall reaction rate law should be. Now, that includes the intermediate oxygen, O, so that isn't what we really want to have. So why doesn't it work? First of all, it doesn't match the experimentally determined rate law, which was, if you look on the previous page, the rate law was the rate is equal to K times O3 squared over the concentration of O2. So it doesn't match the rate law. So that means that it really can't work. But also, in addition to that, it contains the concentration of the intermediate, which we don't like to include intermediates in our overall rate laws. So what we can do is we make an assumption. By removing out the concentration of the intermediate and making the assumption, we can make the rate law match the experimentally determined rate law. So we do this by assuming that the rates of the forward and reverse reaction in the first step are equal. This is our first case of equilibrium. We touched on it in Chem 1, and we might have said it a little bit so far this year, but this means that the initial reversible fast step is at equilibrium, so the rates are equal to the rates. Okay, so just a little hint for yourself. Equilibrium means that the rate of the forward will equal the rate of the reverse. So let's derive that from our rates that we wrote before. So before I said for the forward reaction that the rate is equal to K1 times the concentration of O3. And I said before that the reverse reaction, the rate is equal to K to the negative 1 times O2 times O. Okay, well, the whole point is to get rid of the oxygen intermediate from this rate law. Okay, so what we're going to do is when they're at equilibrium, the rates are equal to each other, so rates are equal. So if we set these two parts equal to each other, then we have K1 times O3 concentration is equal to K negative 1 times O2 times oxygen. Since the rates are equal, we can set those two parts of the rate law together. Now, what we're going to do by substitution and assumption, let's solve for our intermediate and then plug that into the rate law that was produced from the second step, the rate determining step. So solving for the oxygen, so we're dividing this over. So then that means that we have K1 times the concentration of the ozone over K negative 1 times the concentration of the O2. Okay, so now let's substitute this in for right here of this rate law, where, and I guess, I'm sorry, this should be K2 because technically it's from the second step, so it is a different K. So the rate is equal to K2 times K1 times O3 concentration over K negative 1 times O2 concentration. And that's all plugged in for the oxygen intermediate. So then we still have the concentration of the ozone multiplied as well. Okay? Well, simplifying, the K's can just be simplified for the overall reaction. So we don't have to have numbers on our K's anymore. It's just going to be a regular K. And so, you know, all these K's are combined. Then we have two ozones, so we're going to say ozone squared over oxygen gas concentration. And that right here matches what we initially saw from the data that was given right at the beginning, where we had the O2 as the product concentration in there, and that was not normal. But because we were able to derive how it matched, then that, making that assumption and assuming that the rates are equal to each other, then this does agree with the rate law. So since this new rate law also gives the correct overall stoichiometry, it's an acceptable mechanism for the decomposition of ozone to oxygen. So let's see an example of a multiple choice question with this. So considering our equation for nitrogen monoxide plus oxygen gas to make nitrogen dioxide, the following mechanism is proposed, where step 1 is a fast reversible step and step 2 is the slow step. So that means that step 2 would be our rate determining step. Okay, so that's slow. So theoretically, our rate law should match that. Now, let's just see which of the following statements is true. First of all, I know that A is not true because step 1 is not unimolecular. Remember from our molecularity table, if we have a coefficient in front of there, that's really like A plus A to make the products. So that really means that it is bimolecular, not unimolecular. So that tells me right away that A cannot be the correct statement. Okay. Now, for B, increasing the concentration of nitrogen monoxide will decrease the overall rate of the reaction. If you're adding more of this in step 1, then if you have too much of it, the whole point of equilibrium arrow is that you will shift to produce more of the other side. So by producing more of the N2O2, then we can follow in with step 2 and produce the product that we actually want to find. So that is not true because it will actually increase the overall rate of reaction, not decrease it. If you're adding one of the reactants, that'll increase the rate to make it go faster. Okay, then raising the temperature will have no effect on the numerical value of the rate constant. The rate constants are dependent on K, or on temperature. They're temperature dependent. So that is not correct. Dependent on temp, sorry. So that is not a correct choice either. So the last one, which it better be true, is that the rate law is consistent with the mechanism as shown for that. Now, let's derive this to make sure that it does match in fact. Okay, so I didn't really leave myself very much space, sorry. But here, let me quickly add a slide. Okay. Now we got some room to work. Okay, so for our step 1, the forward reaction rate, because it's reversible, remember, so we're going to say K1, just like we did before, because this is for step 1, is times the concentration of NO. Now, remember how we said before that this is not true because it's actually bimolecular? Well, if you look back in your notes at the table for molecularity on page 2, when it's bimolecular, then the rate law has to be squared. So this is just a prediction. Remember, it's all based on experiment, but because there were 2 NOs, we're going to square that. Like so, okay? Then, for the reverse reaction, so this is for the reverse reaction, the rate is equal to K-1 times the product, which is N2O2. Okay? So then at equilibrium, the rates are equal. Rates are equal. So if we set the rates equal to each other, then that would be K1 times NO squared is equal to K-1 times N2O2. Okay? And now the rate law for step 2 is rate equals K2 times N2O2 times O2. And technically the rate law should match this because step 2 was the rate determining step. It's the slow step. But we can include an intermediate. So from our first reaction right here, let's solve for the intermediate. So divide your K over. So N2O2 concentration is equal to K1 over K-1 times the concentration of NO squared. Okay, seeing this, remember the K's, when we plug them all in, the K's they all form their own K for the final reaction. So what this is showing me is since they are on opposite sides of the equation, the NO squared is directly proportional to the N2O2. So that means that they can be directly replaced in the rate law. All right, so then when we replace it in this rate law for the N2O2, we get that the rate is equal to K, and that we're going to just make it our generic K, but we're replacing the NO2 the NO squared for the N2O2, and then we have times the concentration of O2. So this rate law that we have derived from substituting matches the rate law that's said in D. So D is the correct answer for that.